The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thanks for joining us for today's webinar titled Siting Solar in Distribution Grids. My name is John Bernhardt, and I'm Outreach and Communications Director with the Clean Coalition. Before we jump into today's webinar, just a few quick housekeeping items. First, this webinar is being recorded and will be made available on the Clean Coalition website. Also, we will have some time towards the end of this presentation for some question and answer. So to ask a question, in which we're going to batch these together and we'll ask them at the end of today's webinar, you can use the control panel screen, which should probably be on the right-hand side of your computer. And if you just go down to questions, you can type in your question and then we'll compile those. Hopefully there'll be lots of great questions, and we would definitely want to save 15 to 20 minutes for Q&A. And if we don't get to your question, we apologize in advance, but that's probably because there's a nice healthy amount of questions and we'll have to sift through those. So today's webinar has been produced in partnership between Fierce Energy and the Clean Coalition. Fierce Energy is a leading source of energy news for energy industry executives. And the Clean Coalition is a nonprofit organization whose mission is to accelerate the transition to renewable energy and a modern grid through technical, policy, and project development expertise. We drive policy innovation to remove barriers to procurement and interconnection of distributed energy resources, such as local renewables, advanced inverters, demand response, and energy storage. And we establish market mechanisms that realize the full potential of integrating these solutions. The Clean Coalition collaborates with utilities and municipalities to create near-term deployment opportunities that prove the technical and financial viability of local renewables and other DER. Recently, the Clean Coalition was engaged by Southern California Edison, an investor in utilities serving around 5 million customers, to develop a solar siting survey with the objective of making local solar a viable component of the Preferred Resources Pilot, which is known as the PRP. The PRP is an effort by Southern California Edison to study and demonstrate how distributed energy resources, including local solar PV, may support local reliability needs. During this 1-hour webinar, Greg Thompson, Programs Director at the Clean Coalition, and Bob O'Hagan, Program Engineer at the Clean Coalition, will discuss our work doing the Preferred Resources Pilot Solar Siting Survey. Just real quick, so you guys have a sense for who Bob and Greg are. Greg has over 15 years of experience developing and deploying innovative and successful data and software solutions for large utility-like industries. Recently, Greg spearheaded the Clean Coalition's Community Microgrid initiative in collaboration with utilities, and he's authored a seminal paper defining DER optimization methodologies, and was a leading contributor to the CPUC's, which is the California Public Utility Commission's, draft ruling on distribution resource planning requirements for California utilities. In his recent past, Greg delivered an industry-wide application platform plan and financial opportunity while Vice President of Advanced Product Development at Comcast Cable, the largest cable operator in the United States. Bob O'Hagan oversees the development of tools and processes that allow high penetrations of distributed generation while maintaining and improving distribution grid reliability and resilience. His career includes designing telecommunications and test equipment and operations management for both public companies and startups. He's now bringing his skills to clean energy and the power system. Bob has an MS from Stanford in electrical engineering and an MBA from Santa Clara University. With that, I'll hand it over to Greg and Bob to get started.
Great. Thank you, John, and welcome everyone to our webinar on siting solar in distribution grids. And so I'm going to start with a little bit of context, so where solar siting surveys fit in terms of the bigger picture, and then I will talk about solar siting surveys and our methodology around that, and then I'll end up with some specifics on the solar siting survey project we did for Southern California Edison as part of their Preferred Resources Pilot area. So I'll jump ahead here. As John mentioned, the Clean Coalition's mission is to accelerate the transition to renewable energy and a modern grid through technical, policy, and project development expertise. And today we're going to be going into the project development side of the Clean Coalition efforts. Our 2020 objectives are, from 2020 onward, all new electricity generated in the U.S. will come from at least 80% renewable sources and 25% local renewable sources. And by 2020, policies and programs will ensure the successful fulfillment of the above, reflecting the full value of local renewable energy and a modern grid, and including economic and environmental and resilience benefits. We have a few expertise areas in our work with utilities. I'll start from the left here. Analysis and planning. So the solar siting survey I'll be talking about today is part of that. We also do full cost and value analysis of solar, other distributed generation, and other distributed energy resources. And we've done that work for utilities such as PG&E here in California, PSE&G, which we're working on now on a community microgrid project with them in Long Island in New York, and Southern California Edison. We also go deep into grid modeling and DER optimization. We use advanced power flow modeling techniques to showcase how we can optimize distributed energy resources in communities. And we've done that work in detail with PG&E, which they've validated, and we're also doing that work with PSE&G in New York. In addition, we do program design, so we design procurement, so wholesale procurement and interconnection methods, so that we can get a lot more renewable energy connected at a broader scale. And we've done that work with LADWP, Fort Collins, PSE&G, the city of Palo Alto. We do a lot of feed-in tariff design, for example. We did some parking lot solar canopy work with the city of Palo Alto. We work on RAM and REMET improvements, Rule 21 and FERC, and all sorts of stuff just to get local renewable energy deployed more readily. And if you roll that all together, essentially, we bring that all together into our community microgrid projects, where we design and help implement community microgrids, and I'll talk a little bit more about that in a second. So we're doing that in San Francisco with PG&E and our Hunters Point project, with PSE&G in Long Island for the Long Island Community Microgrid Project, and we've done some work in the U.S. Virgin Islands as well. So our vision here, and this is what all of this really means, is getting to a distributed, integrated grid with a lot more local renewable energy, combining distributed generation, whether that's solar or wind or biofuel, with storage as needed and as optimal, with home energy systems, with enabling a lot more electrical vehicles. As we all know, we are on a path towards electrifying our transportation so that we can reduce greenhouse gases with transportation as well as with our electrical grid. So you put all that together and you have a much more distributed and integrated grid that can achieve the goals that we need in terms of greenhouse gas emissions, and as well as better efficiencies and better costs for communities when it comes to our electrical grid. So how do we achieve that picture? The Community Microgrid Initiative is an effort that proves that we can reach that distributed integrated grid through high levels of local renewable energy, and that provides a reliable and cost-effective foundation for the modern grid we're working towards. There are four real objectives for community microgrids. Number one is to get to 25% or more of the total energy consumed locally as local renewables, and that is also maintaining or improving the reliability of the local grid. We are proving the technical and economic viability of community microgrids using a replicable model. So that's the advanced power flow modeling and the cost analysis that we do, and that achieves cost-effective outcomes for communities. We work to accelerate and scale deployments of community microgrids through our strong partnerships with utilities and with the vendors that provide the technologies as part of the solutions. And finally, the final objective is to strengthen local economies. And so community microgrids bring in quite a bit of local investment. They stabilize energy prices by using renewable energy technologies as opposed to other, obviously, commodity options for energy, and with providing an overall system cost that's lower than the conventional method for consuming or producing and distributing energy over the transmission grid. And the result is really a smarter distribution grid featuring more clean energy now, improved grid performance, and stronger long-term economics. So we're going to dive into this a little bit deeper. So what is a community microgrid? The formal definition that we provide, and there are lots of microgrid options out there that are being considered and deployed. A community microgrid really is a coordinated local grid area that's served by one or more distribution substations, supported by high penetrations of local renewables and other distributed energy resources. So to differentiate a microgrid from a community microgrid really spans quite a wide area in the community through one or more distribution substations. It's a new approach really for grid operations. It achieves a more sustainable, secure, and cost-effective energy system, and it also provides long-term power backup for prioritized or critical loads. And really the substation level foundation of a community microgrid facilitates cost-effective replication for optimizing grid operations and customer satisfaction across utility service areas. And essentially, you can think about it as a renewables-based electrical system that spans an entire community area and that utilizes existing utility distribution grids and operations. And that's how we get to the scale and the cost effectiveness we need to achieve a more sustainable, reliable, and secure energy solution. So how do we get to scale with community microgrids? Well, basically what we're doing here is we're defining local capacity targets, and we'll get to how solar siting surveys achieve that. But once you go into a grid area, a community, a substation area or substations, you can look at that and define your target for local renewable energy and other distributed energy resources. And then you can basically create a plug-and-play model for these energy resources. And that's how you get to scale. And that helps us with cost comparisons versus centralized generation. So if you look at this picture here, these are really examples. So these are not literal, but these are examples of if you plan for local capacity, you can actually plug that in bulk, essentially at scale. So whether it's 15 megawatts, which might get you to 15% of the total energy as local DG, or 30 megawatts, or 45 megawatts, or whatever the number is, you're basically planning for that capacity and plugging it in, and you might have cost-effective storage supporting that. You might use demand response as part of that. Your higher cost one on the right might island critical services, right? So you're going to have a little bit of extra cost in providing some islanding for critical loads. We know that's extremely important on the East Coast. So these are different ranges of plug-and-play models for achieving scale and lower costs using our community microgrid initiative. And then this gets into really what we're going to dive into today in more detail, which is our solar siting survey. So we use 4 steps to achieve a community microgrid deployment. And the first step, of course, is looking at the area to find out what's the potential. How much distributed generation is available in a particular community or substation area? And we use a methodical and complete survey of the distributed generation potential within a target grid area. And it's obviously specific to actual site characteristics. And so we'll look at the solar potential, we'll look at is there biopower, is there local wind available, what is available in that particular area. And that mix of local energy resources really is the first step to take, because that will help define the other requirements, such as energy storage and control systems that are needed for that community microgrid. The second step is taking the results of that DG survey, that distributed generation survey, and using that in a DER optimization modeling approach. And so this defines the optimal and most cost-effective portfolios of DER. So with your generation that's in an area, where do you want to really use that, and how do you combine that with the local grid characteristics, such as the power flow, the local customer load shapes, using things like connected feeder capacity to help balance local generation with the local loads. Essentially, we're looking at this grid area and modeling the most amount of local renewables we can use combined with other distributed energy resources in a way that's optimal and cost effective. And again, you have to look at the local characteristics of loads and feeders to get to the most optimal outcomes. Combined with step 2 is step 3, where we are looking at the financial analysis of the DER portfolio. So this is a full analysis of the costs and the benefits and the net value, and this includes reductions in transmission and distribution grid investments, and also includes our recommendations for bulk procurement, that plug-and-play model, and interconnection that achieve additional efficiencies and scale. And then finally, we will end up with a full design and deployment plan. So this is the system design and the operational plan for the community microgrid based on steps 1, 2, and 3, where we have defined the most optimal distributed energy resource portfolios for an area, looking at energy, looking at finances, and looking at the resource in a community, the solar, the wind, the biopower, and we'll come up with a design and a deployment plan to achieve that community microgrid. We also, as mentioned earlier, we work with technology vendors, so if there are specific criteria, design criteria, and operational requirements for a community microgrid, we'll have a sense of which technologies are a best fit for that. And the result is that we can deploy, or the country, any utility, any community in the country can deploy distributed energy resources at scale in months rather than years. So we're really creating a massive acceleration of what today is sort of a one rooftop at a time approach. So now we'll dive into more of the details for today's webinar. So solar siting surveys for community microgrids. So the solar siting survey objectives are to provide an estimate of the solar generation potential in a target grid area that is served by a substation or substations. And we look at the larger solar opportunities, such as sites that can generate, let's say, 250 kilowatts of power or greater. So we're looking for basically what's the real solar potential, the resource in a community that can be taken advantage of, and that's sitting out there waiting for utilities and communities to leverage as part of the electrical system. When we do a solar siting survey, we have really 3 deliverables. We provide an overview and summary in Word or PowerPoint or both. We provide the actual data itself. So this is the Excel file that provides the detailed data per site, as well as the summaries to provide the overall summary and the amounts per categories of solar in the area. And then we also provide a map. And so this is a Google Earth file. It's an interactive map, and I'll be going to this map later in this webinar and showing you that. But it basically displays the grid area. We use sun icons for all the sites that have been surveyed, and you can click on each sun icon and that will provide more information, and I'll be showing that to you in a little bit. So our methodology for doing the solar siting survey is really 5 things. So we identify the appropriate sites in both size and position, including rooftops, parking lots and parking garages, as well as brownfield areas if they exist. We narrow down the candidate sites to the most feasible locations using estimates that exclude, difficult or overly cluttered or overly shaded areas, and so we're using the lowest hanging fruit, if you will, in terms of rooftops and parking lots, parking garages. We measure the most feasible rooftop square footage on a candidate site. Then we calculate the solar potential in kilowatts per site. And then we also include logical groupings where it makes sense, such as office parks or shopping centers, places where there's a single address, multiple buildings, and together those buildings and parking lots will get us to the numbers we're looking for. And on the right of this slide, you can see a picture of the map that I'll be showing in a little bit, and as well as a picture of the Excel spreadsheet showing all the sites, their addresses, the square footage that's been measured, and the output per site. One of the things that is obviously important about the solar siting surveys is finding the most opportune locations, if you will, for solar. And this is where we have looked at a lot of commercial and industrial sites and realized that they're just a great match. And there are really 5 reasons for commercial and industrial locations being a great match with solar. And you can see the son there with his sunglasses on and his thumb up. He's saying, yeah, these are great places for me to to create some energy for your communities. So essentially, these 5 things are: you can get the most generation out of these sites, the larger rooftop and parking lot spaces generate more energy. Those larger systems mean lower overall costs to install the solar systems. So that's lower cost overall system costs for for installing on those large rooftops and parking lots. They also correspond to the best grid locations typically, so they usually have large loads, so they're served by more robust feeder segments, which means once you go through a power flow model, you realize that that's where you can get more two-way power flow, local generation. So there are fewer issues with the local grid by putting out a lot of solar in those locations. They also typically match the load profiles of those sites, and so there's the commercial and industrial sites for the most part have larger daytime loads, and that matches, of course, solar generation during the day. So you're causing fewer issues, less issues on the grid by having the generation match the load. And then finally, these locations, these customers are financially motivated because they have large bills, including demand charges, and in some cases they have rooftop leasing opportunities. So for any community microgrid, any community, any utility looking to leverage the most out of a local energy resource in the form of solar, these 5 reasons are a reason to create programs focused on the commercial and industrial sectors. So now I'm going to go deeper into the solar siting survey that we did for Southern California Edison. And our objective was to do what I've just described across Southern California Edison's preferred resources pilot area. And this was for sites, they wanted us to do focus on sites 500 kilowatts or greater. Now the PRP area is approximately 120 square miles in Orange County, California. And it's bordered roughly by Santa Ana in the north and Laguna Niguel in the south. And this is a picture of the map that I'll be showing in a little bit. I'm going to read this. This is an overview of the Preferred Resources Pilot. So Southern California Edison's Preferred Resources Pilot is focused on meeting customers' electricity needs reliably and safely using clean energy resources. So this will give you just a background on the PRP program from Edison. So SCE is conducting a significant scale multi-year pilot to investigate and demonstrate how the integrated use of clean energy resources, including energy efficiency, demand response, renewable distributed generation, and energy storage, collectively referred to as preferred resources, may simultaneously meet demands for electricity and reduce the needs for incremental conventional power plants to serve customer needs in the PRP target region. Southern California Edison seeks to assess the capabilities of preferred resources while informing the development of the grid of the future and contributing toward California's progressive environmental and renewable energy goals. The PRP is focused on a transmission-constrained area of SCE's service territory served by the Johanna and Santiago substations in central Orange County. More than any other part of the SCE territory, the future power supply needs of this region have been directly influenced by the closure of the San Onofre Nuclear Generating Station, SONGS, in 2013, which resulted in the loss of 2,200 megawatts of reliable power to the region. So given that context, you can see how there's an opportunity here for using distributed energy resources to satisfy the needs of the area based on the closure of songs. So we were engaged by Edison to look at the solar potential as one of the first steps towards the PRP needs. And in doing so, SCE provided two files, and so I'm going to dive deeper into some of the details of this solar siting survey. So we were able to take the preferred resources pilot map as a KMZ file, which defines the boundaries of the PRP areas. And the PRP area has two sub-areas, 24 and 59. And that's a detail, but it helps us organize the solar siting survey and the results of that survey. So we had a version that was available with transparency on a polygon fill color, essentially so that we could use the preferred resources pilot map with Google Earth and match those two essentially. We also had a interconnection map which identifies the substations and feeders in the PRP area. And that allowed us to do an important thing for solar developers, which is to identify the closest feeders to the actual sites. And as part of our results, we provide that information, which tells solar developers which sites are actually close to which feeders, and that helps reduce costs if you're closer to feeders for installation. Here is the summary of our PRP solar siting survey. Essentially, we found over 160 megawatts of new solar PV technical potential that exists in the PRP area, and this is across rooftops and parking lots and parking garages. There was one brownfield area that we identified. This summary, this is just a picture of the Excel summary spreadsheet. I'll just talk through some of the highlights here. So the PRP solar potential by PV size, and so we organized the results in terms of sites greater than 1 megawatt, sites between 500 kilowatts and 1 megawatt, and sites below 500 kilowatts. And those sites that are below 500 kilowatts are included because they're part of logical groupings such as office parks or shopping centers. So the top box here are the results based on the sizes. So it's 164,000 essentially kilowatts of total potential in the area, broken down into the two sub areas of the PRP, 24 and 59. And then if you look to the right, you can see that the sites that are one megawatt and above were about 56 megawatts total. And then between 500K and 1 megawatt, which is the third box to the right, is 67 megawatts. And then less than 500K is the 40 megawatts. So it's broken down into those categories. The bottom box is by type, and so these are the totals for the rooftops, the parking garages, and the parking garages are essentially multi-story parking structures enabling rooftop-style mounting, and then parking lots, which would be ground mounts, and then brownfields. So we had about 89 megawatts on the flat rooftops, about 23 megawatts parking garages, almost 50 megawatts in parking lots, and then about 1.8 megawatts for the one brownfield location. So that gives you a summary of the total of 160 megawatts, or over 160 megawatts broken into these different high-level categories. So our observations from that, essentially there are more opportunities available from structures that are less than 1 megawatt versus greater than 1 megawatt. And that's due to the earlier slide where the common commercial and industrial segments, based on their building sizes and their parking lot sizes, that's essentially the sweet spot. The other observation is that the parking lots and the parking garages represent a potential that is about 75% of the rooftop potential. And this is because most of the large commercial buildings have adjoining large parking lots. And then, of course, putting solar PV in parking lots provides an additional benefit, shade for cars. And often PV-covered parking lots at schools and colleges are the first to be occupied because of that shade. So there's an additional benefit from solar canopies and parking lots. I'm going to get a little bit into some details here on how we rated and how we calculated the amount of solar per site. So we used a density rating. We looked at each site and gave it a rating based on whether that site could have high density of solar panels, medium density, or low density, depending on the clutter that was on that rooftop or how the parking lot was arranged. Essentially, the parking, well, we have a density rating for parking garages that is high because on parking garages, essentially, there's no need for fire truck access between parking rows, for example. So what we did here was we worked with some tools that are available, like helioscope. We would measure different density rating rooftops and parking lots. Then we would talk to local developers to validate those results, and essentially the local developers are the ones who know really what you can get out of a particular type of rooftop or parking lot. And then we would go ahead and work on and look at all of the locations in an area based on the knowledge we gained from the tools and from talking to local developers. So I'll give you examples of this. So here is an example of a high density rooftop. So this is minimal roof clutter. The grouping, is pretty well grouped. There's minimal setbacks and maintenance access. So you can get, we think, in this area, 7 watts per square foot out of this type of rooftop. A medium, there is some roof clutter. There's more setbacks and maintenance access needed. And so this is a lower or a medium density example, so 6 watts per square foot here. And then a low density example would be these two, where you've got lots of skylights, a lot of open space. This one on the left, upper left, looks like a Tetris game. Or there's lots of unusable space and more setbacks and maintenance access. And this is where we would call this low density, so 5 watts per square foot. And here's an example of a shopping center. So there's a Costco, a Kohl's, a Walmart in this shopping center, and there's a low density rooftop at the Costco and a high density one for the Kohl's there in the middle, and then sort of a medium at the Walmart. So you can get these different density levels based on the rooftop clutter, and that helps us calculate more accurately what the realistic potential is for any particular site. And then just to give you an example of the outputs here, so one of the outputs is the Excel file. So this is detailed data per site, including the site address, the site type, the density rating, the viable square feet that we measured, the PV potential per site, the distance to feeders. We also were able to get the available feeder capacity. So this helps developers know that if there's a particular amount of capacity, that might be an easier place to get an interconnection approved versus places where their capacity is already filled up, essentially. The summary tab contains all summaries and breakdowns. All the data fields are explained within the file, and this can easily be filtered by city, by zip code, by type of structure, etc. And I'll note that this, for the Southern California Edison Solar Siting Survey, this file and also the map is available on our website, as well as the summary files, which there's a presentation in PowerPoint and a Word document. These are all available on our website. And I will be jumping to the map in a second. But essentially, the map provides the area that was surveyed. It's in Google Earth. It is interactive. The sun icons mark each potential PV site. Clicking on the sun icon provides more information. And I'll show you what that information is in a second. And all the data that is displayed in the Google Earth file comes from the Excel spreadsheet, so it's all tied together. And you can see here an example in the picture here of a site that's basically 1.8 megawatts. We have the address for the site, the square footage that was measured, the type of structure, so this is a flat roof, the PV density potential, and this one is medium. It's in PERP area 59, and then there's the distance to the two closest feeders there. So I'm now going to jump out of the presentation and put that away, and I'll show you the map. So this is the map that this is a result of the solar siting survey we did for Southern California Edison. You'll see this is Santa Ana up here. That's the northern sort of border. Down here, Laguna Beach, Laguna Niguel down here, sort of the southern area. And this is all the sites that we surveyed that are 500 kilowatts or above, and in some cases are groupings of sites that equal that or surpass that. All of these sun icons are locations, and I'm going to just dive in a little bit here. These are all locations that we surveyed, and I think I'll go over here and find a nice location for us to look at. Let's see what we can find here. We can click on any of these. Aha, there's an airport icon. Let's look at the airport over here just for fun. So this is, I'll click on the, this is the about 4.6 megawatts of potential from all the sites at this address. So this is the John Wayne Airport. Here's the address. Let's look at the individual locations. So here is about 1 megawatts of potential PV capacity on parking garage C at the airport, and that's the address there. The PV area is 155,000 square feet. This is a parking garage. The PV density potential is high, and here's the distance to the two closest feeders, so it's basically sitting on one of the feeders there, so it's very close. So let me actually get a little closer to this one, and we can take a look at this. So there's the airport, and this is the garage here. Let me get a little closer. So you can see this garage here with about 1 megawatt. Here's another garage or parking area here at the airport. Click on that. About 1.3 megawatts of capacity. This is parking garage B2, about 190,000 square feet of solar area, high density. Here's the distance to two feeders. So you can see how you can go through this map and find locations based on each of these suns has the amount of solar capacity, solar potential that we measured. You can go through the map and really do this on all these locations that we've measured. I'll pick another spot over here. This looks like a shopping center, so we'll take a look at that. There's two shopping centers across the street from each other. So we can go in and let's say pick this rooftop. 780 kilowatts. This is a Target in Tustin. The PV area is 130,000 square feet. It's a flat roof. The density potential is medium, and then it's right close to a feeder. So that's a good location. If you add up all these rooftops and parking lots in this side of the shopping center, it's about 3.7 megawatts total for all those sites. That's these sites over here, and then over on the other side is about 3.8 megawatts if you look at the potential across the rooftops here that have been measured as well as the parking lots. So that gives you an idea of how to use this map and what you can get out of it. And you can just essentially look at the entire PRP area and dig into any locations that look interesting and find the solar potential, the location, the address, and distance to feeder, and hopefully that gets people off and running. So that's essentially the presentation for today, and we can hand this off for questions.
All right. Thank you very much for that presentation, Greg. And we had a number of questions come in, so we'll do our best to get to all of those. First off, there are a number of questions about is this interactive map available online, and also is this webinar being recorded? The answer to both those is yes. The full recording as well as the slides will be available on the Clean Coalition website, which is www.clean-coalition.org. And also all of the materials that Greg showed here in terms of the interactive map and the solar siting survey overview that he alluded to, that's also publicly available on our website, and we will be sending out an email to everybody on this webinar with links to both the recording as well as the PRP solar siting survey. So to get into some more content-specific questions here, we'll just jump in. We had a question come in. Is the capacity that you're referring to, Greg, is the nameplate capacity in AC or DC?
That's AC.
Perfect. Getting into question number 2. So the word local can be interpreted in a variety of ways. Whether it be along political jurisdiction boundaries or whatnot. In our view, how are we defining local energy?
Yeah, that's a great question, and we think of local as anything that's below the substation, so anything that's on the distribution grid, and a local area can be defined as one substation or multiple substations. It depends on what the utility or the community wants to do, and in this case, of course, Southern California Edison wanted us to look at the entire PRP area as the local opportunity for renewable energy, for solar in this case. So it really can vary, and I think it's important to define that area, that target area that a utility or a community wants to look at, so that you really can contain it to something and get a concrete deliverable out of that area, which we hope would be a total community microgrid, starting with a DG survey or a solar siting survey.
Perfect. And Greg, I know you had mentioned when giving a visual of the map, the interactive Google Earth map, around distance to feeder capacity. Can you just provide a little bit more color and insight to the interconnection features and overlay that's provided in this map, which is going to be really useful for guiding projects to places where interconnection is going to be lowest cost?
Yes, and in the map itself, we provide the distance to the closest feeders, and that's one metric that's important. If a site is a long way away from a feeder connection or feeder, it can be more costly, of course, to have the interconnection. We also provide in the spreadsheet information about capacity, feeder capacity. So that's a second metric. So if you have a site that has, is close to a feeder and there's capacity available on that feeder, there's a really good chance you're not going to have any issues getting that site approved and interconnected. On the other hand, of course, if it's a distance away, you've got to run some extra, lines to connect it, and there's not any headroom in that capacity there, then it could be much more costly to get that approved and interconnected.
Great. And do you mind elaborating just a little bit on how the feeder distance was calculated? And it might be worth just showing that overlay, if that's easy to do on the Google map.
Bob, are you there? You want to chime in on that? I don't know if I can show that in this.
You have the overlay on there. Anyway, even without that, I can talk to it. SCE gave us a map that showed the different feeder runs, and we highlighted them, and we did not have the transformer locations, so this was just a bird's eye estimate to compare distance from a reasonable point at a reasonable corner of where the solar array might be to where the closest connection on that feeder line was. And basically you find a lot of them that are close to zero, which means the indicated feeder line ran right under the building or the location for the array, like you were seeing back on the airport examples. And as you mentioned, the whole idea was to see what's available, what its capacity is, and if there were two nearby that looked reasonable, we showed both of them.
Great. Thanks, Bob.
There's a lot of information we didn't have for this quick survey, so we wanted to provide as much information for people to move forward with.
And when in the midst of the survey process that you guys were grouping both parking lots and buildings, such as a shopping center, how did you decide to group them? Was it based on an individual property owner, or was it based on just proximity of buildings? Could you speak to that?
Yeah, it was based on obvious relationships. So shopping centers usually have a single owner. Most of the buildings are probably leased. And in a lot of cases, we saw cases where some of the stores had already put up solar, such as Macy's, Costco, and we emphasize that those are the little informational buttons that you see on the map. So there are several corporations that are already aggressively pursuing this. Staples is doing it as well, even on some of their smaller retail stores. So we looked for logical groupings. There were some industrial parks we did not tackle because the individual rooftops were well below the 500K minimum we were looking at, and we were not sure if they had the same owner, even if the architecture looked the same. So that would be the next step. But there are a lot of cases where there were clusters of buildings that would easily produce 30 to 50 to 80 kilowatts. That would be very nice. And we also found a number of parking garages in downtown Irvine that were just below our 500 kilowatt threshold in obvious business parks where the buildings themselves were not good candidates, but those pristine parking garage roofs were very eligible, but they typically didn't pass our 500 kilowatt threshold. But there's a lot in the 250 to 400 kilowatt range there.
Great. Thanks for clarifying that, Bob. And just to make sure that everybody heard, and I know this was mentioned on one slide, but the PRP solar siting survey only looked at potential solar sites that were 500 kW and above. And we did find, and maybe Bob, you could speak a little bit to this around kind of the estimation methodology, but we did find that the siting potential for projects 50 kW to 500 kW was expected to be about 3 times as great. Can you add a little bit of color to that?
Yeah, and it's for the reasons I was mentioning earlier. There are some, especially in the newer built-up areas, you tend to find more flat, uncluttered roofs. A lot of the older structures have a lot of pipes and junk going on them. We also looked at some tools that are emerging to help do these kind of estimates, and most of them seem to way overestimate because they don't take roof clutter into effect. They're very good at assessing nearby shading and those types of effects. They all ignore ground-based parking lots. Some of them will give you parking garages, but the ones we've looked at so far, we felt way overestimated. We wanted to give a conservative estimate that if you see a number there, it's a good starting point, and you can probably get better. And that's why we also had those examples showing Costco's done a great job of fitting solar panels in around their extensive use of skylights. So even though they have low density, they've really figured out how to pack it in, and they're a great example of a company that's pushing forward with that. Even in the low density areas, it still makes sense for them.
Great. Thanks, Bob. And we've had a variety of questions come in. They've been worded a little bit differently, but I think they're all kind of getting to the same point. And that's, so now that all of these potential or prospective solar sites have been identified within Southern California's PRP, what's the incentive to actually get these property owners or businesses to participate and actually capitalize on this opportunity? And what does that model potentially look like? Is that going to be privately owned? Is that going to be utility owned? Do you guys want to speak just a little bit? And maybe, Greg, this question is more geared towards you.
Sure. Yeah, and we look at this somewhat objectively, and we look at a community microgrid and the potential for solar and other distributed generation as a combination of, a utility program with a PPA for wholesale procurement of large opportunities, such as what we did here for Edison. So, the 500 kilowatt and above. Maybe they would even go to 250 kilowatt and above, since there's quite a bit of opportunity there as well, as Bob mentioned. That combined with, behind the meter, typical net metered, customer owned or customer leased opportunities. So we don't particularly think that one is better than the other, although we are pushing for quite a bit of wholesale distributed generation, because we think that model makes a lot of sense for scaling renewable energy in communities and for supporting the objectives of a community microgrid, where we want to reach, at least 25% of the total energy consumed as local renewables. And so that's our take on it, and we're really happy to see Southern California Edison looking at a procurement model for a whole bunch of solar opportunities in the area that would engage the sites and the developers who would provide solar for those sites.
So getting back to the actual production of the survey itself, I know, Greg, that you mentioned kind of the high density, medium density, and low density rooftop potentials. Could you talk a little bit about, how you created those buckets or categories, and what tools did you use to help establish those different criteria?
Yeah, I think, Bob, do you want to take that?
Oh, can you repeat the question about the criteria, John?
Yeah, so rooftops were divided into either high density, low density, or medium density for their PV potential. Do you want to talk about how you went about establishing that methodology, and what outside tools, if any, that you used?
The outside tools we used were solar developers and their eyeballs. So we showed them some sample rooftops and asked what would they do in doing a quick assessment. And these were guys who had, in fact, I mentioned Staples. One of the guys we talked to had actually put solar on Staples. And that's where we learned about the difficulties of the clutter and how these emerging tools overestimate. So we went through some examples to kind of calibrate. That's why we showed them in the slide deck, to give people a relative sense of it. Again, this is a starting point. It's a survey. It's not a detailed design. We didn't care what kind of panels they were using. We just wanted to say, here are large swaths of low-hanging fruit that you need to go after, because big flat roofs that are relatively uncluttered and parking structures are just waiting to have solar mounted on them. There's no significant impediments to moving on.
Thanks. So we had a question come in around, obviously working with SCE, that we are working together with SCE on this endeavor, but how do we go about doing a similar analysis for a utility that wouldn't necessarily want to share any of their grid data?
Well, we can do this same exact thing without providing, distance to feeder or information about feeder capacity. It would be a little bit less valuable to the developers without that information, but you would end up with essentially the same, target areas for lots of solar potential in a community, the same map, the same data, minus the feeder information.
Perfect. And then I know we're getting tight on time here, so maybe we'll wrap this up as the last question. But how would a city or community kind of initiate or request doing a similar study like this? For example, somebody who's based in Minneapolis, where they have a new partnership with Excel Energy, but having an opportunity to actually have that municipality be the primary driver in this kind of study. Can you guys talk about how folks can get involved and learn more about bringing a solar siting survey to their local community, local grid area?
Yeah, definitely. We would love to engage in doing a lot more of these, and in fact, we are working with or plan to work with some of the tools that are out there that can make this go faster. And so we could engage and help, and we can talk about our methodology. We can talk to local developers. We can certainly talk with the utilities, which we do quite a bit of anyway, and design and define the local area that should be surveyed, and then we can go ahead and conduct that survey. So please reach out to us if you have any interest. Let us know. We'd be happy to talk to you about it. We have a long-term goal as well as helping to move the tools industry forward so that these can be done, as I mentioned, faster and across a lot more areas. And we would love to engage in a few more of these so we can help accelerate the industry in that area too, which just teaches the world to fish rather than fishing for them. And so that would be a huge plus to move all that forward.
And how would they get in contact with you, Greg?
You can reach us through, I'm Greg at clean-coalition.org. And you can also go to our website and you can look at our community microgrid initiative, some information there. You can download these files that we showed you in the PowerPoint summary, and I think our contact information is on that as well. And so, let us know if you're interested. We'd be happy to engage.
Well, thank you both very much, Greg and Bob, for your time today, and thanks to everybody for participating and listening in. As I mentioned, you will be getting an email with links to the recording, the slides from this presentation, as well as all of the solar siting survey materials that we produced through this engagement with Southern California Edison. And have yourself a great day, and hope to see you next time. Bye-bye.
Thanks, everybody.